Hi all, as promised, here is a presentation that will go over select questions and their answers to the worksheet for the gas laws. Gas laws are much more straightforward than the stoichiometry, and I will just give you some rundowns of the more complicated questions. Here is question 1. It deals with the volume, initial pressure, and what will happen to the volume if the pressure is increased. Basically, what you would anticipate is that if you increase the pressure, the volume of the gas would shrink. And the law that relates pressure with volume is Boyle's law. The worksheet has all the laws listed that apply to the worksheet and the class in general. Boyle's law is P1 times V1 equals P2 times V2. We want to know what V2, the final volume, is, so we need to solve the equation for V2 equals P1 times V1 over V2. Plug in your values. V2 equals, and make sure that when you read these questions that the units match. You don't want to have milliliters for one unit and liters for the other, and for pressure, millimeter mercuries and torr. Can't mix those. They have to be able to cancel each other. So if there are given in different units, you have to go and do unit conversion before you can solve the equation and get the answers. V2 was, the P1 was 300 millimeter mercury, times V1 is 300 milliliters over the final pressure, 400 millimeters mercury, equals 180 milliliters. And that would be the answer. Not complicated. Interpreting, you have to interpret basically a written question written in words rather than, as I wrote out here, the values already. I separated the values out of the written question. That's probably the hardest part, is to interpret that into usable math. Okay, this one was kind of one of the easier ones. So let's go on to the next question. Alright, here is, as I said, the next slide, question number 3. A gas has volume of 5 liters at 3 atmospheres. If expanded to 7,500 milliliter, what is new pressure? As I mentioned on the first problem, make sure that when you have it, that you have the same units for all, so that they can cancel each other out. Here you have 5 liters, and the other one is 7,500 mils. Those don't match, so you have to do your unit conversion before you can continue with the question. So 7,500, I'm going to convert that into liters. 7,500 milliliters times what relates liters to milliliters is 1 liter is 1,000 milliliters. Milliliters will then cancel out. We're going to end up with liters. Basically 7.5 liters of that. And we're looking at volume and pressure. That would again be Boyle's law, except for we want to figure out what's the new pressure. As you look at this logically, if you expand the volume of a container, the gas will essentially have more room to roam around in as compared to before. Therefore, the pressure should reduce. Hopefully our answer will show that. All right, Boyle's law, Boyle again. By the time you're done with this, you'll have all the laws memorized. P1 times V1 equals P2 times V2. We want to know what the pressure is, so we have to solve for P2 equals P1 times V1 divided by P1. Plug in all these values. P2 equals, pressure was it 3 atmospheres? Yes, 3 atmospheres. 3 atmospheres times initial volume was 5 liters divided by 7.5 liters. And if you calculate that out, you'll get 2 atmospheres. I may not be consistent with significant figures. That's not the object of this exercise. This is meant to go over the gas laws. But actually, 2 atmosphere is the proper significant figures, because the 5 liters limits you to 1 significant figure. The 3 atmospheres limits you to 1 significant figure as well. So 2 being 1 significant figure is the proper answer for this one. All right, on to next slide. Question 5. Now we have something different. This relates volume to temperature. And the law that deals with volume and temperature is Charles's law. Charles' law. And as you increase the temperature, that will increase the volume. Alright, so V1 over T1 is the same as V2 over T2. And here, as I mentioned last week, or in lecture, that when you're dealing with temperature, you want to use Kelvin, because Kelvin is linear and starts at 0 for the lowest possible temperature, and then just goes up by an increment of 1. So when you're dealing with temperature in gas laws, your best bet is to go and convert to Kelvin. And Kelvin is offset from Celsius by 273 degrees. And we started out with 45 degrees C plus 273 degrees, converts that to Kelvin, makes it 318 Kelvin. I think that's correct. And we want to figure out what's the new temperature. And did it say something about that it needs to be in degrees Celsius? Yeah, okay, it wants to be in degrees Celsius. So we have to then convert back once we get the new temperature. And of course we have to solve the equation for T2. Let me see, I'm kind of losing space here. T2 equals, got to move this around, V2 divided by V1 times T1. Okay, so V2 was 400 milliliters. 400 milliliters. Those units are the same, so I don't have to do a conversion. Over V1 is 350 milliliters. So the volume changes. That means I'm assuming and predicting that the temperature has gone up. The volume changes to 4, and so it's expanding. meaning you would have to have it at a higher temperature to make the gas expand. And the 318 Kelvin equals I had to pause this for a second because I didn't have my calculator ready. Alright, so what I came up with was 363.4, which is, this is exceeding the significant figures that we need. 363.4, that's a K right there at the end for Kelvin, which of course is not the answer that we wanted. We want to go from Kelvin back to Celsius, and as I said, not consistent with sig figs here, to which, because it's a subtraction and addition, you can't go past the decimal point of the information with the lowest number of decimals, which, because the way I have it here, is 273 degrees Kelvin, and also the 45 degrees Celsius does not have a single decimal, so we are stuck with just whole numbers. And that, if you subtract this I believe, let's see, minus 273 equals 90.4 Celsius, but we cannot support that decimal, and our final answer would actually be 90 degrees Celsius. So, interestingly enough, if you double your temperature from Celsius point of view, you would not double the volume. As you know, that you go from 350 mils to 400 mils. That's why you have to work off the Kelvin scale, because Celsius is skewed. It has this offset. So if you look at the Kelvin temperatures, it's not doubled. You went from 318 degrees Kelvin initially to 363. That's why it's super important. When you deal with temperatures, you have to work in Kelvins. Alright, so that would be question 5. Question 7. That one is a long question. It's dealing with Maybelline Cousteau, who has a dive tank that reads a pressure of 900 millimeters while she is in her boat. And as she dives down, and that's at 27 degrees Celsius, as she dives down to something that's minus 180 degrees Celsius, which is of course not realistic, but it's for the purpose of creating a question, I suppose. She goes down to a temperature of 183 degrees Celsius. What would be the new pressure in her tank? Again, this deals with temperatures, so you want to make sure you're working with Kelvin, and the law that relates pressure and temperature is Montan's. Montan's or Gay-Lussac. They both figured out this law and were given credit for it. P1 divided by T1 equals P2 divided by T2. We want to figure out what's the new pressure, so we have to solve this for P2. P2 equals P1 times T2 divided by T1. Convert your temperatures to Kelvin. 27 degrees Celsius plus 273 degrees makes Kelvin. That would be 300. 273 plus 27 equals, yes, 300. Didn't trust my math in my head too much today. That's Kelvin. Kelvin, by the way, does not have a degree symbol. and the new pressure at minus 183 degrees. Minus 183 degrees Celsius plus 273 equals 273, basically minus 183. That would be 90 degrees Kelvin. Right, plug this in. P2 equals P1 was 900 millimeters mercury. Mercury times T2 was 90 degrees. Oh, I got a 90 degrees Kelvin divided by T1 was 300 degrees Kelvin equals, actually that would be 3 times 90, that's 270 millimeters mercury. Let me check. Maybe I am going to try to be fairly consistent with significant figures. Kelvin, the 90 degrees Kelvin would only be 2 significant figures, which is fine because that's 2 significant. Our answer is actually only 2 significant figures as well, because the 0, unless I placed a dot there, would not count as being significant. So since I'm not putting a dot there, 270 actually only has 2 significant figures, and that would be the answer for that. So the pressure, of course, goes down. As you're chilling something, the gas will be more condensed and the pressure will be less if you have the same size of container. Actually, I just went back to look over the questions on the worksheet, and I noticed the previous question, question 6, the gases in a hairspray can at a temperature of 27 degrees Celsius and a pressure of 30 pounds per square inch. That is just a regular pressure unit, pounds per square inch. So the approach is the same as for question 7, where you use Amonton's law, and I need to notice I did not write the name of the law in this slide here, but that's Amonton. Hold on, Amonton. So question 6, you do the same thing. You're relating pressure and temperature, and that's also Amonton, and make sure you go and use Kelvin temperatures and just deal with the pressure with the word unit as is, just as if it were a torr or a millimeter mercury. It's a fraction, pounds per square inch is a pressure unit, so they will cancel out the pressure units once you plug that in. So that was it. I just realized that. Okay, now on to question 8. This is a little different. This says, I summarized it for this slide, but it says a gas has a volume of 39 liters at STP, standard temperature and pressure. What will its volume be at 4 atmospheres and 25 degrees Celsius? Question mark. Notice that you're relating actually temperature with volume and pressure. In the previous ones that we worked on, you only had 2 variables changing, and then based on that you're supposed to figure out what happens to the other. Here there's 3 variables, as I said. STP stands for standard temperature and pressure, so you have standard temperature is given by STP, which is actually, STP means you have a pressure is 1 atmosphere. Let's see. I'm sorry, this should actually go into what happens if you do change the temperature and the pressure to 4 atmospheres. So STP is 1 atmosphere initially, and 0 degrees Celsius. 0 degrees Celsius. So that's the initial condition, is actually 1 atmosphere, 0 degrees Celsius, and your final pressure and temperature is 4 atmospheres and 25 degrees Celsius. So you're increasing the pressure and you're increasing the temperature. So what's the volume? We can't use the laws we've been using. The one law that we can use that deals with those 3 variables is actually the, let me switch my colors because I wanted to use green for solving and purple for question. So the law we need here is the combined gas law, which combines all these laws into one combined gas law, which is P1 initial, P initial times V1 initial volume divided by T1 initial temperature is related to final pressure times final volume divided by final temperature. What do we want to figure out? The volume. So we need to solve this whole thing for V2. So make sure V2 is on, let me see if I can squeeze it here at the end. I'll try. V2 equals, so essentially we have to leave P1 times V1 over T1, leave that intact just like it is, but we have to move the P2 and T2 over to the other side. So we divide by P2 and multiply by T2 times T2. That gives us V2. And so plug this in, V2 final volume equals. And one more thing. Again, as we're dealing with temperatures, that needs to be in Kelvin. So this one relates to Kelvin to 273 Kelvin. And this one is 273 Kelvin plus 25 equals 298 kelvins. I'm kind of running into things. All right, P1 was 1 atmosphere times V1 was, oh, sorry folks, V1 was 39 liters times, or divided by T2, I'm sorry, divided by T1. T1 is 273 times T2, which is 298. I'm getting sloppy with units. Kelvin. Divided by P2, which was 4 atmospheres. Once the units cancel, we have the atmospheres. we are left with the unit of liters, which is volume. So that's a good news. So calculate this out. 39 times 298 divided by 273 divided by 4 equals 10.6. I hope I did this right. 10.6 liters, which of course that's too many significant figures, so actually rounded would be 11 liters of volume. And let me double check if that is actually the answer that's expected. Yes. So yeah, just this one is a little bit different because you had 3 variables that were changing. You were increasing the pressure and increasing the temperature. So that should, in both cases, well, the pressure should reduce the volume, the temperature will increase the volume. And so you have to do the calculation to figure it out. You can't just easily look at this from a logical point of view. All right, and on to the next question. Question 11. That one is a pretty cool one. It goes 50 grams of nitrogen N2 gas, basically has a volume of how many liters at STP. STP again is information that gives you what the temperature is and what the pressure is. STP, standard temperature and pressure, indicates that you're having a temperature T of 0 degrees Celsius or 273 Kelvin, no degrees. And the pressure for that is P equals 1 atmosphere. And here you have 50 grams of nitrogen gas. Oh boy, what do we do there? We need a law that somehow helps us relate mass of a gas to something we can work with, some gas law. And the best gas law that can work with this is actually Pivnart. And let me double check in my... yeah, it's on the kind of towards the... Well, it's the last gas law actually that I list on the worksheet. Pivnart is P times V equals the ideal gas law, nRT. Ideal gas law. Gas law. I did not give you a value for R. R is a constant, and I did give it to you on the PowerPoint, or the, yeah, of course, the PowerPoint and the slides for the last lecture, my scribble slides. There's a whole bunch of them depending on what units you want to work in. Looks like we're going to be working with atmospheres, kelvins, and moles. So we need a unit that relates R in those units. This is the ideal gas law constant, 0.082. Time, the unit of that is liters, volume times atmospheres, divided by Kelvin, temperature, times moles. I believe the units that, or the R values that I gave you for the gas scribble slides will say K with a superscript of -1 and moles with a superscript of -1. That is simply means that you divide by K and you divide by moles. That's how you interpret those superscripts. It just means a division. They're below the division line. So now I think we pretty much have everything that we need to plug in. Oh, wait, and we need to figure out the 50 grams, because we can't work from grams. We have to get from grams to moles, because Pivnart deals with moles. So 50 grams of N2. We want to get rid of the grams, and we want to relate that to moles, so we have to use the grams to mole conversion factor. This is N2, gas. I mean, it's gas. It's not the atom itself, nitrogen atom. It's N2 molecule. So we have to double the molar mass for nitrogen, which is 14. But because it's N2, we have 28 grams. So calculate that out. 50 divided by 28 equals 1.79. I'm going beyond sig figs here. 1.79 moles. We'll reduce that towards the end once we're done with the calculations. What did we need though? Okay, senior moments here. Gas, what the N2 gas has what volume at STP? Oh, okay, so we want volume. So we need to solve Pivnart for volume. V equals P. No, I'm sorry. P needs to be moved over. V equals N times R times T. Divide that by P. So N we just calculated was 1.79 moles times R is 0.082 liters times, I'm going to be slow here with units, and so this is your division, kelvins, moles. These units belong still to R, but I'm writing them on the division line as where they need to be, times T. T was 273 Kelvin, because it's STP, 273 degrees Kelvin. What else do we need here? P. P was 1 atmosphere, so actually we don't have to do much with that. 1 atmosphere. We just needed to cancel out units. So we want to end up with a volume, so moles cancel, kelvins cancel, atmospheres cancel. We end up with a final value for liters once we calculate this out. 1.79 times 0.082 times 273, 39.97 is what I got. 39.97 97 liters, which, what are we limited to? 50 grams. Actually, the way it is written, at least on the slide here, is actually we only have one significant figure. Okay, that's a little bit low. I should have probably written 50.0, or at least give us 3. Then I didn't give you the right value for R, so this is kind of bungled up. So let's assume that's 2 significant figures on the grams of nitrogen, and then my R constant is okay with 2 significant figures. So we'll end up basically having to round this to 40 actually two significant figures, or 40 liters, which is, for the purpose of doing the math, 40 is a good answer. I'll be happy with that. Alrighty then, so that would be kind of a little different one. Question 11, that involves moles and a different law, the ideal gas law, Pivnard. Alright. There is a follow-up to this question, which is actually question 12. 100 grams of oxygen, O2, gas is added to the previous information, the previous condition. What is the volume of the combined gases at STP? Basically, again, you know how many moles of nitrogen gas there are. Now you need to figure out what the moles are of the oxygen gas, and that becomes then your new value for N, the number of moles. So just a hint for how to deal with question 12. Question 13, that I talked about in lecture, the density of a gas is the same as, well, density is mass divided by volume. So we have the density of the mass of a gas, which is the molar mass, and we also have the volume that 1 mole of gas has. A mole of gas is Avogadro's number, or not Avogadro's number, but 1 mole of any gas is 22.4 liters at standard temperature, not standard ambient temperature and pressure, but standard temperature and pressure, which is 0 degrees Celsius. Ambient, I think, was 25 degrees Celsius, and the pressure was a little bit less than the regular atmospheric pressure. So anyhow, the density, so you just have to divide molar mass by the molar volume. 14 has to do with Dalton's partial pressure laws. P1 plus P2 plus P3 all the way up to however many pressures you have will then, of the individual gases, will add up to the total pressure. And so I'm not going to calculate that one, but essentially you just have to add up the pressures there. That's 14. What's the partial? Number 15, blast furnaces give off, that's all extraneous information you really don't need. You have a total pressure of 0.99 atmospheres, and you have partial pressure for carbon dioxide and a partial pressure for hydrogen sulfide. Basically, the difference between those two and the total pressure will then give you the remaining pressure, for which is due to air. 16, that is the mole fraction that I was talking about in lecture as well. You just apply the percentage to the total pressure, and that gives you then essentially the partial pressure based on the percentage of oxygen that there is. So how many moles? 17. How many moles of gas occupy 98 liters at a pressure of 2.8? That's just Pivnard, and you would solve for number of moles. Okay, 18. Alright, that's the one I actually wanted to talk about, 18. This one is a little icky. It also deals with number of moles. We also have a volume, we have a temperature. The law that combines all that into something usable is Pivnard again. PV but we have multiple gases, so we actually have multiple pressures, partial pressures depending on the number of moles. So we have to basically calculate the pressure that each gas exerts in that mixture. So we have to solve this. Oh, and then we have 25 degrees Celsius. With gas laws, you have to convert that to Kelvin. 25 plus 273 equals 298 kelvins. So that we have, and we have, we want to figure out what the pressure is. So we have volume, which is 30 liters. We have the temperature, and we have R, which is 0.082. And then all these crazy units here again, liters times atmosphere divided by Kelvin divided by moles. So pressure for, what is the gas? Oxygen, O2, is 5 moles, related to 5 moles. So the P, of course, you solve for P by dividing by V, so it's nRT divided over V equals number of moles is 5 for oxygen, 5 times 0.082. I'm running out of space here. Let me reorganize this for a little bit. Hold on. I moved the values for the Kelvin calculation, and I moved the value for R out of the way, so it's not going to get into my units. So it's 0.82 liters times atmosphere divided by Kelvin divided by moles times 200, and that's temperature 298 kelvins, and then I've left off, this is 5 moles up here for the oxygen, 5 moles, and the liters, how many liters do we have there? 30 liters goes on the bottom, 30 liters times. So let's see, the units will cancel out. Atmosphere is what we want. Kelvins cancel. Moles cancel. So all you have to do is multiply 5 times 0.082 times 298 divided by 30, and you're ending up with a partial pressure of, for oxygen, of 4.07, which is too much in terms of significant figures, but I'll just leave that for right now. 4.07 atmospheres due to oxygen. You repeat the same thing for nitrogen, N2. And there you had 3 moles. So 3 moles times 0.082. Crazy units for this guy again, times liters times atmospheres divided by Kelvin divided by moles. Also in 30 liters. And then the temperature also is 298 kelvins. Again, the kelvins cancel, the moles cancel, the liters cancel. Oh, and yeah, kelvins cancel. I'm sorry, liters cancel. Okay, we got everything canceled. The only thing that doesn't cancel is the atmospheres, which is fine because we want to have pressures. This one is due to the oxygen, so we'll do the same calculation. 3 times 0.082 times 298 divided by 30 equals 2.44 atmospheres. And this is Dalton's law of partial pressures. Basically, P total then. P total is the partial pressures added up, 4.07. And I'll fix the significant figures here. 2.44 atmospheres. I can't. I'm spastic. Sorry, it was a long night. Both are in atmospheres. ATMs equals 4.07, 6.51. I think so. 6.51 atmospheres. However, let's fact check. We had given 3.1 decimal, basically. I need to actually do a real assessment of all this. We would have had to two significant figures from the moles which are involved in the multiplication. So this would have had to have been 4.1 actually for the oxygen, and then similar thing for the nitrogen, 2.4. That means then the total significant, adjusted for the proper significant figures, would be 6.5 atmospheres. That one was a little tough, but it's a good question. I'm glad I was able to show it to you as an example. Question 21. I kind of skipped through 18. Question 19 is okay, balloon. I'm backtracking here for a sec. Question 19, we have 35 liters of helium, 20 degrees Celsius, and 45 degrees Celsius. What's the new volume? So this one is straightforward, just relating volume with temperature, nothing too exciting there. Question 20, we have a tank of volume at a temperature and pressure. So there's 3 pieces of information there. But there isn't a before and after condition. If you had a before and after condition, you would, and plus there's numbers of moles that's asked. So the only proper gas law that can help you with that is Pivnart. And since it's asking for a number of moles, you have to solve that equation for n, the number of moles. Okay, 21 now, back to 21. This one also deals with moles, so you are going to automatically jump to our favorite equation, ideal gas law, Pivnart, nRT, and we are supposed to figure out what's the temperature in degrees Celsius of the balloon. So we need to solve Pivnart for T. T equals P times V divided by N and R. And we have moles, 3.5 moles. We have 85 liters. and 1 atmosphere is the pressure, and we are going to have to, because the gas constant is in kelvins, so we have to then convert our answer from Kelvin. That's what we're going to get. R is 0.082. And yes, total senior moment here. Liters times atmospheres divided by Kelvin divided by moles. Kelvin moles. Alright, I think we're set here. And 85 liters. So plug in T equals 1 atmosphere is the pressure. We have volume was 35 liters. 35 liters divided by 3.5 moles divided by R. So R is times 0.082. What's on top of the fraction stays with the 0.082 times liters times atmosphere. What's below needs to get shifted up, because if you're dividing by division, it's basically a multiplication. So the Kelvin and the moles go to the top. And hopefully the units cancel to where you end up with a temperature of K. So we got to end up with K. All right. Moles cancel. Liters cancel. Atmospheres cancel. So we just have to plug this in. 35, 1 times 35 is 35, divided by 3.5 divided by 0.082 equals 121.9. I'm going to round this to 122 kelvins, and hopefully something is wrong here. Oh dear, okay, I'm sorry. It's not 35 liters, it's 85 liters. Oh, 85 liters. I gotta redo the calculation. Okay, 85, let's do this over. 85 times 1, so don't have to do anything, divided by 3.5 divided by 0.082 equals, that's more like it, 296 Kelvin, but they want us to report the answers in Celsius, so 296 minus 273 equals, I should probably be able to do this in my head, but I'm not, is 23 degrees Celsius. So a balloon that holds 85 liters is inflated with 3.5 moles at 1 atmosphere. So what's the temperature of the balloon? All right, good night. All right, on to question 22. That one has a lot of information listed, but it's really not as complicated as it looks at first. So you have calcium carbonate decomposing at 1200 degrees Celsius to form CO2 gas. And that is just the temperature at which it will decompose. And that's what will give you then the 25 liters of CO2 that are collected at that temperature. And what will the volume be after it cools to 25 degrees Celsius? I'm sorry, actually that's the initial temperature. So you have the volume, you have the temperature, and you basically just have to relate volume to temperature. That's it. A little bit more complicated due to the question, the way it's worded. But, okay, so you need V1 to T1 equals V2 to T2, and that should be actually Charles's law. Charles again. Charles. And of course, since the quiz and test and all those are open book, you will not need to memorize exactly which law is what. It's just you need to know which law to look up to then use. So if you're just dealing with volume and temperature, then you are pretty much in good hands if you use Charles. Anything else we need to look at? Yes, we want to convert temperatures to Kelvin again, because it's otherwise not linear. So T1, the initial temperature, is, oh, and then we want to know V2, so I can solve that already. V2 equals V1, oh, sorry, hold on, I'm going to go and stop here and reorganize a little bit to make more room. Alright, I moved Charles's law over a little bit. Okay, we want to, what will be the volume be? Okay, so we want V2 equals V1 times T2 over T1. And as I said, the temperatures have to be in kelvins. So 1200 degrees Celsius goes to Kelvin by adding 273 degrees. That makes that, and I had to move to a different room and I left my calculator. So I'm going to have to stop here again and get my calculator. Hold on for a sec. Alright, I'm back with calculator in hand, which of course for this one I could have figured out by hand. 1473 degrees Kelvin, and then the other one, after it cools to 25 degrees, T2 is T1. So this is 1473 is T1, and my equal sign stinks, equals T1, and then 25 degrees Celsius plus 273 equals 298 Kelvin, and that's T2. And we can plug all this in, and I'm out of space again, so I gotta reorganize that somewhat. Sorry. Shrunk all that down a little bit. Alright, so now V2 equals V1, what was it, 25 liters? 25 liters times T2 was 298 degrees, not degrees, Kelvin, just Kelvin, and divide that by T1, 1,473 kelvins. The kelvins cancel, so calculate out 25 times 298, 25 times 298 divided by 1473 equals, I have 5 liters, something like 5.1, yeah, 5.1 liters. So V2, once you chill this down to normal room temperature, you have actually 5.1 liters of gas. Significant figures look pretty good. The 25 liters is what limited you to 2 significant figures. These are multiplications, so we go by least number of significant figures. Alright, so this would be question 22. Question 23. A helium balloon with internal pressure of 1 atmosphere and a volume of 4.50 liters at a temperature of 20.0 degrees is released. What is the volume at a pressure of 0.6 atmospheres and T temperatures minus 20.0 degrees Celsius? This is basically letting a balloon go into the upper atmosphere. So you're reducing pressure, and the temperature, of course, is chilling as you get higher up. This also is a situation where you are comparing a before and after condition, and you're dealing with 3 variables: the volume, the pressure, and the temperature. For that, your best gas law to look at is the combined gas law, P1, or initial, times V1 over T1 equals P2 times V2 over T2, or you can also say final. The 2 condition is the final condition, and that is called the combined gas law. Combined gas law, which, what's the volume? We want V2 essentially. So we have to solve that for V2, move all the other stuff over, leave V2 by itself. So that's P1 times V1 divided by T1. And then we got to divide by P2 times P2 and multiply by T2 equals. And okay, of course we are given again 20 degrees Celsius for T1. And because we're dealing with gas laws, we have to do that in kelvins. So 20 degrees Celsius plus 273 equals 293 kelvins for T1. Kelvin. T1. T1 equals T2 equals minus 20 degrees Celsius plus 273 equals 253 Kelvin. Alright, so this is our temperature conversion, and I'm continuing on below this. So V2, plug all this in. Pressure was 1 atmosphere. 1 atmosphere. 1 atmosphere times 4.5 liters. And there's actually 3 significant figures here. Times T2, it's 253 kelvins. Divide that by P2, which was 0.600 atmosphere. Looks like they want us to report this in 3 significant figures, except for the way I copied this down. Gotta check the original question. 23. Yeah, 1 atmosphere was also given as 1.00, so that's 3 significant figures as well. And then T1 is 293 kelvins. So we want volume, hopefully everything but liters will cancel out. And multiply this all out, and we'll get hopefully the right answer. Let me see. 4.5 times 253 divided by 0.6 divided by 293. I am getting something incredibly bogus. Must have gotten twitchy finger syndrome here. 4.5 times 253 divided it's when you don't clear out the memory of the calculator before you start. 4.5, let's do it over, times 253 divided by 0.6 divided by 293 equals 6.48, and that's rounded. 6.48 liters is my final answer. And that seems to jive with what I had written down initially when I did these quite a while ago. Alright, 6.48 liters is the size of the balloon once it rises up into higher atmospheres. Less temperature, less pressure. Alright, that's question 23. Question 27. Another one of PivNART, because we are working on moles. So that's kind of your immediate hint that you're supposed to work with the ideal gas law. P times V equals NART, N-R-T. And that's the ideal gas law. And will it explode? Gas cylinder can tolerate internal pressure of up to 210 atmospheres. If the cylinder holding 3.5 moles of gas at a 2-liter volume, that's the volume of the cylinder, is heated to 1,350 degrees Celsius, will it explode? So again, temperatures have to be converted to kelvins if they're not given in Kelvin. So the temperature T equals 1,350 plus 273. Little calculator and no twitchy fingers this time, hopefully, plus 273 equals 1,623. 1623 kelvins is the temperature in Kelvin. So we have pressure, we have the number of moles. So actually we want to know what the pressure is. We know that the cylinder can hold 210 atmospheres, but we don't know what this gas will do at the condition. So we want to actually solve for P. P equals nRT divided by V equals. So we have the volume. The number of moles is 3.5 moles. Oh, and then we have our gas constant. That is R equals 0.08. Never mind. 0.0082. All those crazy units is liter times atmosphere divided by kelvins divided by moles. So that's R. Which I suppose I could have written a little easier. Hold on. Alright, I moved it out of the way. Alright, so R, we have number of moles, 3.5. R is 0.082. Liters, atmospheres, kelvins, moles, and we have squeeze that in, 1623 kelvins. Kelvins cancel, moles cancel. Oh, and liters. Where did the liters go? The liters have to go in the bottom, and it was 2 liters. 2.0 liters. So liters cancel, and all we have now is left atmosphere as a unit. We can calculate that out, and 3.5 times 0.082 times 1623 divided by 2 equals 232.9. That would be the pressure of this gas under those conditions, is 232.9. I'm totally off, and that's atmospheres. Totally off on the significant figures. I only need, or I can actually only report 2 ultimately. However, we know even with 2 it would be 230 atmospheres, and the container can only stand up to 210 atmospheres. So in this case, yes, absolutely, the container would blow up. Container would blow. Container will go kaboom. Will blow. Explode. Okay. Explode. So that was question, what was it, 27. Alright. Question 30. This is the most horrible question of the whole worksheet, I think. It's a nasty one, so that is one of the reasons I am covering it, and I don't expect you to figure this out on your own, but I wanted to show you. Alright, so we have 2 flasks. Flask 1, like this, and there's a stopcock between these 2, so they can be separated. So there is gas 1, G1, and G2. Gas, once they're separated right now in flask 1, there is 2, which is a 2.5 liter flask, and you have oxygen gas at a pressure of 0.7 atmospheres. In flask 2, which is slightly bigger, it has a volume of 3.8 liter, has hydrogen gas, and has a pressure of 1.25 atmospheres. So once the stopcock is opened, gas 1 will go and equilibrate with the side where gas 2 is, and vice versa. Gas 2 will go over to the side of gas 1. Essentially, both gases will, after you open the stopcock, occupy larger volume, so they'll expand and take over the entire volume of the 2 cylinders. So initially, what you have to look at is conditions where you want to know the pressure. So the pressure, you have to look at pressure of the gas before and pressure of the gas after for each of the situation. And that would be the gas law that applies actually for this is P1 over, what is it? What's the law over V1? Is, oh, I'm sorry, P1, that's Boyle's law. Boyle is P1 times V1 equals P2 times V2. And that is for either gas. We want to figure out what is the pressure of either gas after it expanded. And then after you do that, then you work with partial pressures. Each gas, the pressure that it has at the end after it's expanded is a partial pressure in the system. So we want to figure out P2 for each one. P2 of, what is it, oxygen, O2, P2 of O2 equals, we just solved Boyle's equation for P2 is P1 times V1 over V2. The pressure is given initially for oxygen as 0.7 atmospheres. And V1 was 2.5 liters. And V2, after it has allowed to expand, is a total volume of between 2.5 and 3.8, which is 6.3. Where's my 6.3 liters is V2 once they had chance to mix and expand. So we end up with a pressure unit of atmospheres because liters cancel. So 0.7 times 2.5 divided by 6.3. What am I getting here? I am getting 0.2. There's something wacky again. Okay, I must have missed. I'm getting 0.02, but when I did this calculation before, I had actually 0.2. 0.7, let's try again. 0.7 times 2.5 divided by 6.3, 0.28. 0.28 atmospheres. Alright. Oops. So now P2 of, what's the other gas in here? Hydrogen. And if you go and put a light to a match, it will blow up, but that was not the question. So again, P1 times V1 over V2. This gas, the hydrogen, had a pressure of 1.25 atmospheres. Times the volume was 3.8 liters initially. But then once it had a chance to mix, the final volume is 6.3 liters for this gas as well, equals, so 1.25 times 3.8 divided by 6.3 equals 0.75 atmospheres. 0.75 atmospheres. So these are basically the partial pressures of each of the gases in the mix. So then you use Dalton's law of partial pressures to get the total pressure, and essentially all you have to do is add these two pressures together for a total of 13. Oh, I got it. Sorry, I just can't think straight anymore today. 0.28 plus 0.75 equals 1.03. 1.03 total. P total equals 1.03. Since we're adding up atmospheres, we should be okay with supporting 2 decimals there. Yeah, our partial pressures are to 2 decimals because we're multiplying and dividing with values that have 2 decimals, but then when we're adding up, we're limited by the, I'm sorry, I meant 2 significant figures for the multiplications and divisions. And then when we're adding up, we are limited by the decimal places, which we have 2 decimal places, but that means we can go to 1.03 atmospheres on that. And let me double check. Yeah, You know what, I kind of messed up when I initially did this. I only got it to 1.0 atmosphere, so actually we should be able to support that 0.3. Alright, that will be the end of what I'm going to cover. If you do this at home and do the other, I think I did 11 or so, 11 or 12. Plus I covered a couple others not in math, but I at least explained how to approach them. If you still run into issues while doing the rest of them, see me in lab or next lecture, and then I can help you some more. But go and get some practice with that and just get familiar with the gas laws and go through some calculations. Don't forget to convert temperatures to Kelvin, otherwise you get the wrong values. All right, thanks for listening, and have me blab here for quite a while.